Hi, my name is Torsten, and on behalf of my co-author, Harry Osterhaus, I'm presenting our work on non-parametric choice models. Now, the literature has different understandings of what a choice model is. For us, that's a model that quantifies choice probabilities among a set of options. I'll just give you an example. Say we have a user that wants to choose a movie to watch next, and they have exactly 2 movies to choose from, or the option to just not watch a movie and do something else instead. The way we usually model such a problem, this has 2 important properties. First, the person is going to do exactly one thing, and we know which options they have. The way we usually model such a problem is that we assign every option a score, and then apply, say, a softmax function to those scores. In the random utility world, that's also called the multinomial logit model, and that tells you, well, there's probably going to be other models, and that's true. And to understand how those models differ from the softmax, let's just take a step back, drop one of the options, and compute choice probabilities again. That's fine. We can also do that under another model, under the exponomial model. And that's totally okay, it gives us other probabilities, but we could fit both models to give us some desired choice probabilities. Now, the thing is, if we add the second movie back in, something interesting happens. Under the softmax, both existing alternatives cede the same share of choice probability to the new option. Under the exponomial model, the less popular alternative cedes the highest share of choice probability. And that's different with all these models. In this case, the softmax, the MNL, represents more explorative choice behavior, gives higher weights to less popular items, while the exponomial model represents more conservative choice behavior. Now, the problem is that only one of these models can accurately model choice in both cases, the case where we have 2 items and the case where we have 3 items. But in some settings, we would want to find a model with good choice probabilities. For example, if we want to sample from a learned policy, if we need confidence, if we want to decide when to give a recommendation or not. So there are cases where we want an accurate model here. And then the question arises, how do we get the most accurate choice model? And well, we could benchmark different models and just take the one that works best, right? But that's expensive. So it would be much cooler if we could just learn the correct model from data. And that's what we do in the paper. I'm not going to go into details due to the time. But roughly what we did was that we started with a very general equation for choice probabilities. And this is also in the literature by assuming that certain random variables in here are IID, and we do that if we recommend top K items anyway. We arrive at a very convenient integral equation for choice probability. And this integral has item scores in it. We use those already, those are just our logits. And it consists of a PDF and CDF of some random variable. Under softmax, this variable would be Gumbel distributed. It could be anything. And this is also in the literature. What you can now do is when you want to learn item scores, you can also try to find a good form of the CDF and PDF. The problem is that existing solutions don't work with recommended systems, with modern systems, for example, because they're not continuous. So we built our own model, we call it LCM for Rec, and that learns, in addition to the item scores, also the shapes of this PDF and CDF. Again, I don't have time for the details, but feel free to check out the paper. Instead, we'll just skip to the experiments. We performed 2 experiments in the paper. Again, we only have time for the first one, unfortunately, where we checked whether our approach could actually retrieve the correct choice model from data. The way we did that was, well, on industry data, we don't have choice models. Unfortunately, those are not observable. So we just generated our own data. We generated 3 data sets under different choice models. The first one under softmax with a Gumbel distribution. The second one under an exponomial model with an exponential distribution. And the third one under, a Gaussian mixture distribution. There is no model for this because in reality, we also don't assume that users choose exactly like a softmax or any other model. So it could be anything. And then we fitted different models on these data sets, including our own model. And first thing we did was that we compared the plots of our learned distributions with the true distributions. And what we observed was that our model was generally able to fit these curves. Here for the softmax, we're able to fit the CDF pretty well. The PDF has some wobbles. That's due to our parameter configuration, but it's fine. We get the general shape right. For the other model, the exponomial model, we get some higher deviations. Our model still understands what the PDF is supposed to be like, but it's a bit more wobbly. CF also isn't perfect, but it's fine. I'm going to show you in a second why that is not a problem. And then for the last distribution for the Gaussian mixture, we saw that our model can also retrieve that very well. Now, in practice, we care about choice probabilities. That is the result of the integral that you see down there. So we also compared how well we can approximate those. What we did was we compared the probabilities of the true model, because we generate the data, so we know the true model, with the probabilities that the different fitted models provide. And we found that in any case, well, the correct parametric model was always the best performing, that's expected. But our non-parametric alternative was always second and always pretty close to the best parametric model in all cases. And best when there was no true parametric model. This is the best possible outcome for our experiment. Same with negative log likelihood. So we could conclude that we can actually retrieve the true choice model, like an alternative for softmax from the data. Now the literature suggests that it's also easier to rank if you have better choice probabilities. So you see the table keeps expanding. We also compared NDCG and accuracy, and we're surprised to see that all models still fitted the same way. The numbers are pretty high because it's simulated data, it fits our assumptions. You have like transitivity and choice behavior. But we saw that all models were pretty good, and there was no advantage of having a better choice model here. And that was surprising. It was also good news because that means that if you use a softmax, and even if it doesn't match a user's true choice model, if you only care about ranking performance, that's fine. You can just keep using the softmax, and that's good because it's very efficient compared to other choice models. All right, that's almost it. Let me just say we have a poster on discrete choice models and exposure bias. If you want to learn more about that or just chat, feel free to come by. Okay, thank you.
So you made a lot of assumptions for your simulation, right? So how did you come? How did you select what to focus on, and how did you come up with your assumptions?
So with simulated data, you can always find something that you would expect in reality, and that's not on simulated data. We generated very, very general user embeddings, item embeddings, and then let users choose according to our choice model. There's always, so for example, we didn't have a long tail distribution in here. You could do that as well. But we already know that choice models should be able to match that better as well. One assumption that we did was that we used many data points per user, because our goal was to find out whether our assumptions were true asymptotically, right? We also had some experience on bias where that was important. Feel free to check out the paper on that.
What? What would the next step be? I mean, so is there kind of a verification of your assumptions done in large-scale studies? Is this something that you plan?
So there are data sets that include this information, what options the user had, what they choose from, and we're actively working with them. Yeah.
You have the NDCG metric that doesn't seem to have much difference between the different options. So what is it calculated based on, and why it's not sensitive to the recommendation options?
The NDCG metric. That's a good question. This setting, we computed over the choice sets that a user saw, because the user can't choose anything outside the options that they observed. In this case, it's pretty high because we use many observations, and we have a transitive choice behavior, so that would be expected, but that's fine.